This is a car. You've seen millions of them. Next to a pickup, it looks small. And next to this, they both disappear. You've probably never seen one in real life. In a moment, it'll load 400 tons of rock. The truck itself weighs about 280 tons, so it carries more than its own weight every single load, and hauls it down a grade so steep, your car would ride its brakes the whole way. The strangest part, by the laws of physics, it shouldn't work at all. The weight should crush its own wheels. The brakes should catch fire on the way down. The tires should melt. None of that happens. So, how do you build a machine this big that actually works? And one question almost nobody asks. If we can build one this big, why don't we build them even bigger? It all comes down to a single number: cost per ton. Everything about this machine traces back to it. These trucks live in mines, the open pits where we dig for copper, iron, gold, coal, and much more. And in mining, the prize is almost always buried under a mountain of worthless rock. Miners call it overburden. Before you reach even a single ounce of value, all of it has to move. Imagine yourself in charge of that mine. You've got mountains to move and two ways to do it: a whole fleet of ordinary dump trucks, or one of these. The giant looks absurd. It drinks 1,200 gallons of fuel a day, almost a gallon a minute. Forget miles per gallon. This thing measures fuel in minutes per gallon. Yet it wins. In a single load, it moves what a building site dump truck would need more than 20 trips to match. A highway truck, 10. Even a 100-ton mining truck, 4. For all the staggering fuel the giant burns, it moves so much in one single trip that every ton ends up costing less. That's the secret. These machines aren't big to be impressive. They're big because big is cheaper, which is why they just kept getting bigger until they hit 400 tons. Try to push past that, and physics pushes back hard. It all starts with the engine, a monster putting out 4,000 horsepower from a single block of steel. Roughly 4 Formula One cars bolted together. The obvious move? Connect that engine to the wheels the way almost every vehicle does. Transmission, drive shaft, gears, and let it rip. Right? No. Nothing made of gears survives that. 4,000 horsepower clawing against 400 tons of truck would grind those gears to shavings. And the bigger you build it, the worse it gets. So most of these giants do something clever instead. The engine never touches the wheels at all. It spins a generator and makes electricity. That power runs back to motors tucked inside the rear wheels, and they do the driving. No drive shaft, no gearbox. The same trick that moves a diesel locomotive. Except this one decided to haul a mountain. For decades, that was the answer. Every giant did it this way, except one. Meet the Caterpillar 797, the biggest of them all. And the one hauling those 400 tons we started with. When everyone else went electric, the 797 held out. No generator, no motors. Just gears, the largest mechanical transmission ever bolted into a truck, swallowing the full 4,000 horsepower and somehow living to tell about it. Same impossible problem. 2 opposite answers. Both of them work. That was just the first problem. The tires? Worse. Each tire stands over 13 feet tall. Picture 2 people, one on the other's shoulders. The tire's still taller. Just one weighs nearly 12,000 pounds. Every truck rides on 6. Each one carries about 100 tons over broken rock in brutal heat for thousands of hours. For decades, only 2 companies on Earth could build them at all: Michelin and Bridgestone. At $60,000 to $90,000 apiece, a single set runs close to $500,000. And they wear out and get replaced again and again for the life of the truck. None of that, though, is the strangest part. The thing that caps this truck's top speed isn't the engine or the brakes. It's the tires. And not how strong they are, how hot they get. The reason is heat itself. A tire this big can't shed it fast enough. The faster the truck runs, the more heat builds deep inside the rubber with nowhere to go. Let it climb too high, and the tire doesn't just wear out, it fails. Violently. Every tire carries a maximum safe speed, and the mind governs the truck to that limit. The engine has more to give, the tires don't. Remember that word, heat. It turns out to be the quiet villain of this entire machine. Now, tires are only problem 2, because once you've got 400 tons rolling downhill, how do you make it stop? Think about your car. The brakes turn motion into heat, and you slow down. Simple. Try that here, and the brakes would blow smoke and burn through long before the truck ever stopped. Friction alone can't kill this much momentum, not without catching fire. So these trucks barely use ordinary brakes at all. They do something far cleverer, and this is where our two giants split again. Take the electric ones first. Rolling downhill, the truck turns its motors into brakes without reversing anything. The wheels keep spinning forward exactly as before. But instead of the motors driving the wheels now drive the motors, cranking them like a dynamo. A bike light spun by the wheel it drags against. Generating power is hard, so the motors resist being cranked, and that resistance pushes back through the wheels, holding the truck against the slope. The faster it tries to roll, the harder the motors fight it. The momentum it sheds turns into electricity, fed into resistor banks that glow red hot and burn it off as heat. Engineers call it dynamic braking, slowing a machine by turning its motors into generators. The 797 does it differently. It has brakes, but not the bare friction kind on your car. They're sealed inside a housing, with oil pumping through, hauling heat away as fast as friction makes it. The plates still clamp hard, but because that oil carries the heat off, those brakes can hold the truck down a full grade without ever burning out. Something dry brakes simply cannot. Two giants, two ways to stop, one idea underneath. Don't fight the motion with friction alone. Carry the energy away as fast as you make it. And the newest electric trucks don't waste that energy. On some haul roads, they run under a trolley line, a trolley assist system, the same overhead setup that powers an electric train. Braking downhill, a truck feeds its current back into the line to help haul the next one up the grade. The descent helps power the climb. Before any of this, running, stopping, hauling, somebody has to build the thing. And it's far too big to build the normal way. How do you even get one to a mine? You don't. It can't legally touch a public road, and it's far too big to haul in one piece. It doesn't arrive as a truck at all. It arrives as a kit. One 797 broken across a dozen semis. The frame, the engine, the dump body, the cab, and 6 tires that are practically 2 truckloads on their own. Parts roll in from factories spread across the continent and meet in the middle of the mine. A crew assembles it. Cranes, welders, mechanics, on the clock for weeks. Less like building a truck, more like raising a building. Once it's built, it almost never leaves. Moving it means taking the whole thing apart and starting over. These machines are born in the pit, and they stay there for the rest of their lives. Which leaves the only question a mine actually cares about. Is a machine this absurd really worth it? On paper, it's a financial nightmare. Buying one costs between $5 and $8 million, and you can't just order one. Each truck takes a year or more to build. Then you keep it alive. Around $1.5 million a year in fuel, a fresh set of tires worn through in under a year, an engine, driveline, and brakes living under constant punishment, around the clock. They do all this in the cruelest places on Earth. The same model works a desert mine in Chile where it hits 50 degrees Celsius, and another in the far north of Canada, or Siberia, where winter drops past -40. Nearly 100-degree swing. And the machine has to start, run, and haul through all of it. Now, to reach the cab, the operator climbs a staircase as tall as a house. From up there, a single wrong move costs a fortune. And yet they can't see a pickup parked directly behind them. A strange, lonely kind of responsibility. in charge of all that weight, while a good part of the world around them simply vanishes from view. Add it all up and it sounds indefensible. But remember the only number that ever mattered: cost per ton. By that measure, this machine isn't expensive at all. Every dollar spreads across an almost unimaginable amount of material. Load after load, day after day, for decades. For a ton of earth moved, nothing else comes close. It isn't a fuel-hungry money pit, just the opposite. The cheapest way we've ever found to move a mountain. Remember the question from the very beginning: if bigger is cheaper, why not just keep building them bigger? The answer: we mostly stopped. The 797 has sat near the top of the size chart for over 20 years, because past a certain point, the tires can't be built any bigger, the roads can't be cut any wider, and the savings dry up. Physics and economics quietly drew a line, and we're already standing on it. The race stopped being about size. It became about being smarter. Right now, across the world, thousands of these giants drive themselves. No one in the cab. In the iron ore pits of Australia and the frozen oil sands of northern Canada, computers steer them, load them, and haul them around the clock, guided by satellite and sensors, moving billions of tons without a single driver. Not a prototype, not someday, right now. Here's the part that sits close to me. Here in Alberta, Canada. One of the very first 797s went to work in the oil sands back in 1999, built to last 72,000 hours. By 2020, it had run more than twice that, over 20 years of work, more than 50 million tons hauled, and it was still going. Think about that. A machine that shouldn't work at all, too heavy, too powerful, too big to build, not just working, but outliving everything it was ever promised. Quietly, in the cold, far from anyone who'll ever see it. That's the strange truth about the machines that move our world. The bigger they are, the less we notice them. We see the phone, the car, the building. We never see the mountain that had to move first, or the giant that moved it. Until now.